Hi, this is Mr. Barron. I'm going to be showing you how to do 1992's free response question on equilibrium. In this question, it initially makes you start thinking you need a nice table, but it turns out you don't. What it does is it tells you you start off with 100 grams of this guy right here, and that it's heated and decomposes, and it decomposes into a 5-liter container containing the only two gases you're working with are water and carbon dioxide, these two guys right here. And they tell you that the total pressure is 7.76 atmospheres. Now don't forget, according to Dalton's law, the total pressure is the sum of the partial pressures. So I'm going to call this partial pressure A and this partial pressure B. So it's PA plus PB. And the variables that affect how much of each of these are produced, well, if you look at it stoichiometrically, for every water molecule you produce, you're going to produce one molecule of carbon dioxide. And using the ideal gas law, you can assume that A plus B, PA and PB are going to be the same number. So you can take 7.76 atmospheres and divide it in half, and you get 3.88 atmospheres. And that is going to be the partial pressure for water, and it's going to be the partial pressure for carbon dioxide. You can assume this because of that mole-to-mole ratio 1:1, and since you have the same number of moles of gas that are produced from your original 100 grams, and because of Dalton's law, these two should add up to be the same. So I mean, another way to do math is make this equal to P sub A. And that shows the dividing by 2 and giving you the correct answer. So now, I'm going to take this information, because the question's asking for how many moles of water do you actually end up with? Well, we know the pressure, and since we can treat it as an ideal gas, we know the pressure, we know the volume, we know the ideal gas law constant, and we know the temperature. So we can plug in each of those values to find our correct answer. So I'm going to start plugging everything in. So my pressure for water is 3.88 atmospheres. The volume of my container is 5 liters. N is what I'm trying to find, which is my moles of gas. And R is the gas law constant. So for R, in this particular problem, I'm going to choose the R that deals with atmospheres, moles, and Kelvin, because in this particular problem, we're working with all of those units. So it's going to be 0.0821 liters atmospheres over moles Kelvin. Then my temperature has to be in Kelvin. So that's 100 and, what is it? Where's the temperature? 160 degrees Celsius plus 273, which gives you 433 Kelvin. And then you just have to find N. You're just solving for the number of moles. When you do that, your number of moles of water is 0.545 moles of H2O. Notice I'm keeping it to 3 sig figs because you need to make sure you do that on the free response section. There you go, there's A. Now B is asking for how many grams of the original solid remain in the container, assuming everything that you figured out in A. So this you can use stoichiometry, because now that we know the moles of water, we can figure out how many moles and how many grams of sodium hydrogen carbonate are needed to produce that many moles of water. So I begin with 0.54 moles of water. I use my mole-to-mole ratio. I want to figure out how much sodium bicarbonate, sodium hydrogen carbonate. Cancel out the H2O. The numbers come from the chemical equation, so it is 2 over 1. And then I want to figure out the mass of the sodium hydrogen carbonate, because I'm trying to figure out the grams that it took to make that many moles of water. So I add up the molar mass of NaHCO3, and it's 84.01 grams per mole. And I get an answer of 91.57 grams. Now that's not the correct answer. That's actually how many grams of NaHCO3 it took to produce that many moles of gas, which we found in our container. What we have to do is figure out how much solid remains. Remember, we started with 100 grams. So it's 100 grams minus 91.57 grams, and that gives you 8.43 grams of NaHCO3 remaining. And it might be a really good idea on the AP test to make sure you write down that that's exactly what's remaining. All right, C, it asks for the equilibrium expression. The equilibrium expression, remember, only works for things that are aqueous or gases. It doesn't work for solids and liquids. So K sub P this time is just going to be H2O times CO2. And there aren't any exponents because the coefficients are 1. So what we have to do is we have to plug in, since it's K sub P, that means I'm putting in pressure, not concentration. Pressure of water, we figured out from A, was 3.88 atmospheres. That was the partial pressure. For carbon dioxide, it's 3.88 atmospheres. Take those two numbers, I multiply them together, and I get for K sub P 15.05, but don't forget, you want to make sure you keep everything in 3 sig figs, so it's 15.1, and that's your K sub P. Now for D, it says you've placed 110 grams of solid sodium hydrogen carbonate. What's the total pressure? Well, we have a different starting mass this time. Before, we began with 100 grams, and that resulted in a total pressure of 7.76 atmospheres. But remember, the key information is that there was still remaining solid, meaning not all of that 100 grams got converted into that pressure. That means at equilibrium, the maximum pressure that you're going to reach is 7.76 atmospheres. So even if you have 110 grams to begin with, it doesn't make a difference. You're still going to get 7.76 atmospheres as your total pressure. Why? The answer for why is because you had solid left over with only 100 grams. I mean, think about it. If equilibrium would create a greater pressure, you would have had to use up more than what you used up in this experiment. In this experiment, or this reaction, you only used up 91.57 of that 100 grams. So even if you start with 110 grams, you're still going to have only a production of 7.76 atmospheres because that's where the equilibrium lies. If you have any other questions, please let me know.